So good afternoon, students. Today we are going to be discuss about the spectroscopy, that is electromagnetic theory and spectroscopy paper, that is course 6, paper 2. We are going to be discussed. So in this, what we'll do is we will start this spectroscopy first. So in the spectroscopy, that is block 2, which we have. So in the block 2, that is atomic spectra we have, and then we have the molecular spectra block 3, and then after we have a block 4 IR and Raman spectra. These are the blocks which we have belongs to the spectroscopy, and first block is belongs to this electromagnetic theory. So we will start with this atomic spectroscopy, then after we'll move to molecular spectra, then after we'll move to IR and Raman spectroscopy. All these we are going to be moved. So first we will start with the atomic spectra. So before going start into this atomic spectra, that is unit 8, just we'll briefly we'll study about what is spectroscopy and what types of different types of spectroscopies which we have. Just we'll go through briefly about that one. Then we'll start into this what we call this fine structure, in which what we are going to be study, all those things we'll see here. Okay. So then first we will see actually what is spectroscopy here. So we will see. Right. So what is a spectroscopy? What is spectroscopy? We will see here. Right. So here, spectroscopy is nothing but it is a branch of physics only. See, one of the branch of the physics. So we'll write this as a branch of physics we have. This is a branch of physics which deals with the observation and interpretation of radiation emitted or absorbed by atoms or molecules. So in the spectroscopy, what we are going to be seeing means is a branch of physics which we one of the branch of the physics which we have. In this, mostly we are going to be observe the interpretation of the radiation emitted or observed by the atoms and molecules. Okay, so how the energy is absorbed and how the energy is evolved, that is emitted, what processes it is going to be takes place. That is what we are going to be see in this spectroscopy. And moreover, we will see the structure of the atoms as well as the molecules with the help of these spectroscopy, which we are going to be studying here. Okay, so that is about a simple thing which we have. And mostly here in your syllabus, whichever we are going to be have, we are going to be study mainly about atomic spectroscopy. One thing which we are going to be study is atomic spectra. In under this, we are going to be study different parts, and also we have like a molecular spectra. Okay, molecular spectra. These are the main two spectra which we are going to be study here. Okay, first we will study about atomic spectra. So in this atomic spectra, what we are going to be study and all those things we are going to be study here. So under this atomic spectra, so we have like a block 2, which we is atomic spectra. So in this, we are going to be study about this fine structure, which we are going to be study. So in this fine structure, so we will see different interactions we are going to be see here. So first, we are going to be study about this what we call orbital magnetic dipole moment, which we are going to be study here. Orbital magnetic dipole moment. That is nothing but orbital magnetic dipoles. So which we are going to be study here. So about this orbital magnetic dipoles. Okay. So about this orbital magnetic dipoles, we are going to be study here. Okay. So in order to study this orbital magnetic dipoles, so first we will be consider about one electron system. So here we'll study about what we call one electron atom. We are going to be study here about the study of one electron atom. Okay. So here we are going to be continue our study of one electron atom. So in which the orbital quantum number L, okay, in which orbital quantum number L, which determines the magnitude of electron angular momentum. So this orbital quantum number L, it is going to be determines what we call the electron's angular momentum. Determines electrons angular momentum. So L orbital quantum number, it is going to be determine electron's angular momentum. It is going to be determines. Okay. So then here, suppose if you have taken that one electron, okay, one electron we are going to be take here. So this electron will be revolving in an orbit about the nucleus of an atom. Okay. So here, suppose if I take that here, this is what we have. So in this orbital, electron is revolving, right? Electron is revolving around this nucleus with a velocity v here. Okay. So what we have taken here, we have taken that an electron revolving in an orbit. So electron is revolving in this orbit. It is revolving about the nucleus of an atom, about the nucleus of the atom. At the center, we will be having the nucleus here. Around this nucleus, it is revolving. So whenever it is revolving in the orbital, what will happen means it is going to be produces what we call it is a current loop. It is going to be produced. Okay. So in this, electron is revolving around the nucleus of an atom, which is a current loop. Okay, which is a current loop, and it is going to be produces magnetic field here. Understand? It is going to be produce what? Magnetic field here. So it will behaves like a current loop, and it is going to be produces a magnetic loop here. So here we will consider this mass of the electron as m. We are going to be consider. Okay. So here, if we take this, we'll draw this diagram. L will be in this direction. L is going to be in this direction. So here we will be consider that the mass of the electron is small m. We are going to be consider, and charge of the electron is this E we are going to be considered here. So it is going to be moving with the velocity v here. So what we have considered is the electron is revolving around the nucleus in this orbital. So it will be behaving like a current loop, and it is going to be produces the magnetic field. It is going to be produced. So that means it behaves like a magnetic dipole. It behaves like a magnetic dipole. So the mass of the electron, we have taken it as a m we have taken, and the charge of the electron is E we have taken, and the velocity of the electron which is revolving around the nucleus is V we are having. Okay. So
బయట వెయిట్ చేసి
Right. So here we have taken that the electron is revolving around the nucleus in an atom, and this electron which is revolving around the nucleus, it will behaves like a what we call a current loop, and it is going to produce the magnetic field in that one. So as we have discussed that m is the mass of the electron which we have, and E is the charge of the electron, and V is the velocity of the electron which is revolving around the nucleus. Okay, and we will consider that the radius of this orbit. Okay, generally we will call it as a Bohr's orbit we are going to be called. So this is the radius which we have. So the radius of this orbit is R we are going to be taking. Okay, radius of the orbit is R we are going to be taken here. So therefore, as it is revolving around the nucleus, it is going to be behaves like a what we call current loop. So it is going to be produce a current which is having a magnitude of I, which is going to be have. So this I is equals to, we can write it as a E by T we are going to be right here. Understand? So what we did is the current which is produced by the electron as it is revolving around the nucleus. So it will behaves like a current loop, and it is going to produce a magnetic field, and the current which is generated, which is having a magnitude of I is equals to Q by T will be there here. And here T is nothing but this capital T is nothing but it is the period of the electron in the orbital. Okay, otherwise we can say that this T is nothing but it is a orbital period of the electron, orbital period of the electron we are going to call. Orbital period of the electron we are going to be called here. Right. So then we can write this T, which is having here T orbital period. So T can also be written as T is equals to 2 pi R by, we can write here. So therefore, if you substitute T in this I is equals to E by T, we can get it as I is equals to E by, in place of T, what we are substituting is, we are substituting 2 pi R by V. So it will be EV, it becomes EV by 2 pi R, it is going to be becomes. Okay. So the electron, whichever revolving around the nucleus in the orbital, it is going to be generate a magnitude of current I is equals to E by T. And this T is nothing but the orbital period of the time, which is given by T is equals to 2 pi R by V. So therefore, I is equals to, it is becoming it as what? EV by 2 pi R, it is going to be here. Okay. And from the, and we, right. And from the electromagnetic theory, the magnitude of the orbital magnetic dipole moment is given by the magnitude of the orbital magnetic dipole moment is given by mu L. It's given by mu L here for a current I in the loop. So what is that is from the electromagnetic theory, the magnitude of the orbital magnetic dipole moment is given by mu L for a current loop I in a loop of area A we are going to be have. So therefore we can write mu L as mu L is equals to, we can write I into A, we can write here I into A, and this A is nothing but this is nothing but A is nothing but area of the loop we can write here. Area of the loop we can write here. Okay. And its direction is perpendicular to the plane of the orbit. Its direction is perpendicular to the plane of the orbit here. So as we have this one, so here L mu L will be perpendicular to the plane of the direction. In this manner, it is going to be have. So which we can write it as a mu L here. Okay. It is the direction with which it is having. It is perpendicular to the loop. Perpendicular to the loop. Mu L is equals to IA, which is mu L is direction is perpendicular to the plane of the orbit as we have seen here. Okay. Now substituting this area value, A is equals to whichever we have. So we will take A is equals to pi R square. A is equals to pi R square we can take here. So therefore, mu L, what we are going to get it here, it is mu L, which is equals to already I value we have got here, that as a EV by 2 pi R we have got. EV by 2 pi R we have got. And this area, which we can write it as a pi R square, we can write. Area is equals, we are writing it as a pi R square. So therefore, by rearranging the terms, that is R will, one of the R is going to get cancelled and this pi get cancelled. So this we can write it as mu L is equals to EVR by 2 we can write. Okay. What is that? Mu L is equals to, we can write it as a EVR by 2 we can write. Right. Now the electron is having the negative charge. Okay. Electron is having, as the electron is having the negative charge. So that is the reason why here. So the mu L will be in the opposite direction. It is going to be opposite to the direction of the orbital angular momentum. So this L is nothing but the orbital angular momentum. Opposite to this, we are going to be have this mu L as it is having the negative sign here. And this L, which is nothing but the orbital angular momentum, the L, which is so L is nothing but orbital angular momentum, which is given by L value. L is equals to, we can write it as orbital angular momentum as L is equals to mv, or we are going to write here. Okay, so question 2 here. So now we have written this. Now we will divide these two equations. Okay, we will divide these two equations. So we will be dividing this equation 1 by equation 2 here. If we divide, so what we are going to get is, we are going to get it as a mu L by L, which is equals to E by 2M. Okay. So if we divide these two equations, so what is that equation 1 we have is, actually I'll write again here. So this equation 1, right? Equation 1, what we have is this is mu L. This mu L value, that is E V R by 2 we have, and this L value, which is MVR. So it will be EVR by 2 into 1 by MVR. So this RR will get cancelled. So VV also get cancelled. So it will be equals to E by 2M. Okay. So mu L by L is equals to this, you are going to get E by 2M. That is the ratio of the ratio of the magnitude of mu L, the ratio of this magnitude of mu L of the orbital magnetic dipole moment to the magnitude of this L of the orbital angular momentum. So this is what we have, mu L by L, whichever we are having, calling it as the ratio of the magnitude mu L of the orbital magnetic dipole moment to the magnitude L of the orbital angular momentum of the electron, which you are going to get it as a E by 2M. So this E by 2M, whichever we are going to get, it is a constant, right? It is a constant. E is nothing but the charge of the electron, and M is nothing but the mass of the electron which we have, and this is going to be a constant, and it is independent of the details of the orbit. It is independent of the details of the orbit. Okay, the constant here, this E by 2M, whichever we have, the constant E by 2M, whichever we have. So we will be calling it as a gyromagnetic ratio. We are going to be called. We'll be calling it as what? Gyromagnetic ratio we are going to be called. Okay. So for the electron, E by 2M is nothing but gyromagnetic ratio of the electron here. So if you want to note, write this in the form of a vector form, so same equation which we can write, we can denote in the form of a vector notation as mu L, which is equals to minus, because electron is having the negative charge, minus E by 2m and L here. So this is the vector notation which we have. So this minus sign means that mu L is the opposite direction to L, as we have seen here. So this one, as we have seen, L and mu L are both are opposite direction. That is the reason why we are getting this minus sign here. Okay. And the unit of electron magnetic dipole moment is we have like a ampere meter square. Ampere meter square we are going to be have. That is what we have. So this is what the relation between these two we are going to be have. Okay. So then we have like a what we call Bohr magneton also. Okay, Bohr magneton. So Bohr magneton, we have Bohr magneton. Bohr magneton. So from the quantum mechanics, the permitted scalar values of orbital angular momentum L, the permitted values of orbital angular momentum L are given by L is equals to what we have, and L into, that is root of L into L plus 1 we have, okay, into H by 2 pi. That is the permitted values, the permitted scalar values of orbital angular momentum L is given by L is equals to under root of L into L plus 1, L into L plus 1 into H by 2 pi we have. And this small L, whichever we have, this is what we call it as a orbital quantum number we have called. We'll call it as orbital quantum number we'll call. This is the orbital quantum number. So therefore, the magnitude of the orbital magnetic momentum of the electron is given by magnitude of the orbital magnetic moment of the electron is given by mu L, which is equals to under root of L into L plus 1 into EH by 4 pi m. EH by 4 pi m we are going to get. So the quantity, this EH by 4 pi m, whichever we have, the quantity EH by 4 pi m from a what we call natural unit of the magnetic that is measurement of the atomic magnetic dipole moment, which is calling it as a what we call a Bohr magneton we are going to be called here. So generally this Bohr magneton will be represented with mu B here. Okay. So mu B is equal to what we have, EH by 4 pi m. This is what we call it as a Bohr magneton we are going to be called. Okay, Bohr magneton we are going to be called here. So this is what we call the interaction, of the what we call electron. There is nothing but the orbital magnetic dipole moment and Bohr magneton, which we are going to be called here. Okay. So next we will see the behavior of magnetic dipole in external magnetic field. That means how the electron is going to be behave next we'll see the behavior. Okay. So now we'll see the behavior of we'll see the behavior of magnetic behavior of magnetic dipole in external magnetic field, in external magnetic field. external magnetic field. Right. So this is what we have to see here. So when an which this behavior of dipole in external magnetic field, which is going to be leads Larmor precision, it is going to be lead here. So whenever an electron is moving around the nucleus of an atom, that is, electron is revolving around the nucleus of an atom, which is equivalent to a magnetic dipole. As we seen that when the electron is revolving around the nucleus, okay, when the electron is revolving around the nucleus, so we call it as it is going to be equivalent to the magnetic dipole. Already we have discussed this one. Okay, will behaves like a magnetic dipole here. Going to behaves like a magnetic dipole. So hence, when an atom is placed in an external magnetic field, that is, when an atom is placed in an external magnetic field, the electron orbit precedes about the field direction as axis. About the field direction as axis. So this precision is called it as what Larmor precision we are going to be called. We'll be calling it as what Larmor precision. And the frequency of the precision is called Larmor frequency we are going to be called. Okay. So when an atom is placed in an external magnetic field, the electron orbit precedes about the field direction as axis. So this precision is called it as what Larmor precision we are going to be called, and the frequency of this precision is called it as what Larmor frequency we are going to be called here. So here, suppose if you see, so how this is going to be have is in this direction. Okay. So here, draw this the so in this what we did is when an electron is in an external magnetic field, so the direction of the magnetic field, this is what we have. So B will be in this direction. Okay. And here actually we have the orbital which is revolving around the nucleus. Okay. Revolving around the nucleus. So this in this orbital electron is revolving around the nucleus here. Okay. So this we have kept it in the magnetic field here. We have been kept it, which is having magnetic field B. So the orbital angular momentum of the electron is represented by, already we have seen this L is represented by L, which is perpendicular to the plane of the orbit. Okay, which is perpendicular to the plane of the orbit we are going to be have here in this case. Now, suppose if I take theta be the angle between L and B. Okay, theta be the angle between the L and B here. Generally, what happens means here. Right. So this is the theta, and this is what we have L. So this theta is the angle between the L and B here. Now, the orbital magnetic dipole moment, which is mu L, okay, which is mu L of the electron, which is given by, already we have discussed about this one, which is given by minus E by 2m into L we have. Minus E by 2m into L we have. So the negative sign of the indicates that E is the charge of the electron. Minus E is nothing but that is the charge of the electron, which is having a mass of m here. Okay. So the minus sign signifies that mu L is directed opposite to L here. So L is in this direction we have. Now similarly in the opposite direction, you have if I extend this one, you have mu L. Okay. So mu L is in the opposite direction. In this direction, we have mu L here, okay, which is opposite to the direction of L we have. So as a result of its interaction with the magnetic field, its interaction with the magnetic field, the dipole experiences a force, otherwise we call it as the dipole is going to be experiences a torque, which is given by tau. Okay, it experiences a torque tau, and its value is given by mu L cross B we have. Okay, so as a result of interaction with the magnetic field B, the dipole experiences a torque which is given by mu L cross B we have. So mu L is equals to, we know that the orbital magnetic dipole moment mu L is equals to minus EM by 2L. This is what we have. And similarly, the torque which is experienced by this what we call in the magnetic field is given by tau is equals to mu L cross B we have. Okay, tau is equals to mu L cross B we have. So these equation 1 and 2, so the torque tau acting on the dipoles is always perpendicular to the angular momentum L here. Okay, the torque here acting is always perpendicular to the torque tau acting on the dipole is always perpendicular to the angular momentum we have. So that is in this direction. Okay, in this we have torque which is acting is perpendicular to this L always. So actually it should be normal. Maybe in this direction you are going to be perpendicular. Now, so we know that torque causes the angular momentum. Okay, the torque which is going to be causes the angular momentum to change this according to this what we call Newton's law. So we can write tau, whichever we have, we can write it as a dl by dt. We can write dl by dt. And this change takes place in the direction of the torque. The torque tau on the electron, torque tau on the electron, therefore produces a change in dl, produces a change in dl in a time period of dt. Okay, the change dl is perpendicular to this L. The change in dl is perpendicular to this L. Right. So hence the angular momentum L remains constant. Hence the angular momentum remains constant here in magnitude, but its direction only it is going to be changes. So direction it is going to be changes. So as the time is goes on, as the time changes, the vector L traces a cone around D. Vector L, it like in this manner, it as the time is goes on, behaves like what we call a cone here. Vector L, the change in dl perpendicular to L already we have discussed. Hence, the angular momentum L remains constant in magnitude, but its direction changes as time goes on. The vector L traces a cone around B. Okay, cone around B here. So here we will this. Okay, around as the time is changing, it is going to be changing in the cone shape. Okay, in the cone shape, right? So as time goes on, vector L traces a cone around B such that the angle between L and B remains constant. The angle between L and B, it is going to remain constant. That is the precession of L and hence of the electron orbit around B. Okay. So now here, if we consider that here, if we consider that omega, okay, omega it be the angular velocity of precession. Omega is the angular velocity, omega be the angular velocity of precision, omega be the angular velocity of the precision, then L precedes through an angle omega, angle omega dt, okay, in time dt. So therefore, as we take from this figure, so omega dt here, so here one, here. from here to here. So this is angle whichever we have, omega dt, right? So we can write from this figure. So from this figure, we can write omega dt, okay, omega dt. So which we are going to write it as dl by L sin theta. We can dl by L sin theta we can write, because the angle is equal to arc by radius whichever we have. So therefore, we can write this as dl by, that means we can get the omega value, otherwise omega is equals to dl by dt into 1 by L sin theta we can write. Omega is equals to dl by dt into 1 by L sin theta we can write. So which will be equals to this dl by dt is nothing but it is a tau. We already discussed tau by L sin theta we are going to get. Tau by L sin theta we are going to get. So therefore, from that we can write tau is equals to already from the equation 2 we have tau is equals to what we have, this one. Tau is equals to what we have, mu L B sin theta. That is a mu L cross B is there, so that we can write it as a mu L B sin theta. So therefore, we can write the tau is equals to, we have written it as mu L B sin theta is there. So therefore, we can write omega, this omega is equals to, we can write mu L by L into B. We can, okay, omega is equals to, we can write it as what we can write, mu L by L into B we can write. So thus the angular velocity of Larmor precision is equals to the product of the magnitude of the magnetic field B and the ratio of the magnitude of the magnetic moment to the magnitude of the angular momentum. That is nothing but we can write from the equation 1. If you apply this in the equation 1, we will get this as mu L by L, which is equals to mu L by L is equals to, we can write it as a E by 2m we can write. Okay, E by 2m. From the equation 1 which we have seen here. Okay, so here, this one, sorry. Mu L is equals to minus E by 2m into L we have. So there from that equation, we can write mu L by L is equals to E by 2m we can write. So therefore, again, we can get the value of omega is equals to E by 2m into B we can write. Omega is equals to E by 2m into B. So that is a Larmor frequency, or Larmor, from the Larmor precision, we can calculate the Larmor frequency as F is equals to frequency, which we can write it as omega by 2 pi we can write. So this will be equals to, we can get it as a E by 4 pi m into B. So simply we are substituting omega value here. So we will be getting the Larmor frequency as E by 4 pi m into B we are going to be get here. Okay. So here if you see this equation, it is independent of the variation of the angle. That is, it is independent of the theta. It does not depends upon this theta with which angle it is going to be rotate around this what we call L. Okay. And it is not dependent upon the field direction also. So Larmor frequency, if you take it is equal to F is equal to E by 4 pi m into B we have got. So what is the importance of this we have is the Larmor frequency is having the importance in atomic structure. It enables easy calculations of energy levels in the precision of external magnetic field. That means if you keep an atom in the external magnetic field, you are going to be calculate these energy levels we can calculate. So that is what important we have. Okay. So this is about what we call Larmor frequency. Next, we will see the space quantization we'll see here. One minute. So next we'll go for space quantization. Right. Next we'll start this space quantization. Space quantization. Right. So in the space quantization, so when an atom is placed in an external magnetic field B, okay? So whenever we keep this atom in an external magnetic field B, the electron orbit precesses about the field direction as axis. That is axis nothing but Larmor position. Right. So when an external, when we keep this atom in the magnetic field, that is external magnetic field, the electron orbit will be precesses about the field direction, that is an axis, which we call it as a Larmor precision we call it here. So the electron orbital angular momentum vector, that is L, the L, okay, L is nothing but the electron orbital angular momentum vector L, which traces a cone around B here, which traces a cone around B here. That is, suppose here if you take what color, if this electron is revolving around the nucleus, okay, this is the electron orbit which we have. Now what we did is we kept this in the external magnetic field, which is having a magnitude of B here, right? Which is having a magnitude of B here. So now, as we said that the electron orbital angular momentum vector L traces cone around B at an angle of theta here. So at an angle of theta here. So generally it will traces in this manner. So this one, this is the theta. Okay, this is L here. Understand? The electron orbital angular momentum vector L traces cone around this B here in this manner. Okay, with an angle theta between L and B. And this theta is going to be remains constant here. Theta is going to be remains constant here. So if the magnetic field B is along the z-axis, if the magnetic field B is along the z-axis, if you taken, okay, suppose if I take is along the z-axis, if you have been taken, right, along the z-axis, then the component of L parallel to the field, component of L parallel to the field is given by L z is equals to L cos theta. Okay, parallel component is given by L z is equals to L cos theta. So we can write cos theta, so which will be equals to Lz by, yeah, which is equals to Lz by L here. Cos theta is equals to Lz by L here. So quantum mechanically, the magnitude of this angular momentum L and its z component Lz are quantized according to this relations. Okay, according to this relation, what are those relations? We'll see here. So we know that L is equals to what we have is root of L into L plus 1 into H by 2 pi. Okay, root of L into L plus 1 into H by 2 pi. And we know that Lz is equals to, we are going to get it as what? ML into H by 2 pi. Okay, so L value according to this quantized L and that is Z component of L are quantized according to these relations. These relations which we have is L is equals to under root of L into L plus 1 into H by 2 pi. And we have Lz is equals to ML into H by 2 pi here. So here this L and first L, small l is nothing but it is what we have orbital quantum number. So small l is nothing but it is a orbital quantum number we have. The small l is orbital quantum number, orbital quantum number. And also this ML is, it is a magnetic quantum number. It is a magnetic quantum number. ML is nothing but magnetic quantum number we have. So hence the angle theta, whichever we have in between these two, L and B, this angle theta, which is in between this L and B and the Z axis. Okay, hence the angle theta is the between L and Z axis, which is determined by the quantum numbers L and ML. Okay, which is determined by the quantum numbers L and ML. So according to this, cos theta is equals to what we have is, okay, so cos theta, just we have written that cos theta is equals to, we have Lz by L here. Cos theta is equals to Lz by L here. Therefore, we can write this is equals to ML by root of L into L plus 1. Root of L into L plus 1 we can write here. Okay. So since for a given values of L here, for a given values of L, so for a given values of L, there are 2L plus 1 possible values. There are 2L plus 1 possible values we have. Okay, 2L plus 1 possible values which we have. Of ML, which is going to be get like a 0, comma plus or minus 1, comma plus or minus 2, and so on up to plus or minus L. Okay. For a given values of L, 2L plus 1 possible values of ML, we are going to be have that will be equals to 0 or plus or minus 1, plus or minus 2, and so on up to plus or minus L values. It is going to be possible. And the angle theta can assume 2L plus 1 discrete values. Angle theta can assume 2L plus 1 discrete values it is going to assume here. Okay. So if you see this, if you draw the figure, okay, the notation of this, if you draw here, right. So as it is going to be take the different values for L is equals to 2. Okay, for L is equals to 2, for L is equals to 2, if you take, so ML can take the values, ML can takes the values like 0, 1, 2, as well as the minus 1 and minus 2. So ML can take 2, 1, 0, comma, minus 1, comma, minus 2. For L is equals to 2, all the values of ML will be 0, 1, 2, and minus 1, minus 2. Because it is going to be possible 2L plus 1. So total 5 values. 2L plus 1 means 2 into L plus 1, that is 5 values you are going to get. 2L plus 1 values it is going to be possible. So L value, if we substitute 2, 5 different values of ML are possible. Those are 2, 1, 0, minus 1, and minus 2 you are going to be have. Suppose if you see the picture of this one, if we draw the figure which we have, ML value. ML value initially will take it as a 0, and it is having similarly ML is equals to 1, and it is having ML is equals to 2, and similarly it is going to be have ML is equals to -1, and also ML is equals to -2 you are going to be having. So if you see in this, okay, so this value is ML is equals to 0, whichever we have. For ML is equals to 1, this is ML is equals to 1, and similarly we have ML is equals to 2 here. And similarly we have ML is equals to -1, and ML is equals to -2 we have. So for this, it is a 0, and for this one, its value will be -s by 2 pi. Okay, L value. And for this one, it will be -2 into h by 2 pi. Similarly, the value for ML is equals to 1 is h by 2 pi, which we have. And for this one, it will be 2 into h by 2 pi you are going to be getting. Okay. So generally, this will be the along z direction, whichever we have. B is along z direction we have. Okay. So these are the what we call orientations of this orientation theta of L with respect to the field B. With respect to the field B, which is in the along the what we call z direction, which we have along the z direction. So here, if you calculate the values of theta, that is the angle with which it is going to be have. So we studied that cos theta, which we have got it as what? ML by root of L into L plus 1. Understand? Under root of L into L plus 1, which we have got. So there, if you substitute all the values, ML is equal to 2 as well as the 1, 0, -1, 2, if you substitute ML value, for which L values which we have. So we will be getting different values like 2 by ML is equals to 2. We have 2 by root 6 we'll get. And similarly, we'll get 1 by root 6. And we'll get a 0. We'll get -1 by root 6 as well as the 2 by root 6, which we are going to get. Okay. So for different values of L. Okay. So these values, if you see, if you calculate this 2 by root 6, we will be getting the theta value. Theta value is equals around 35 degrees we are going to get. And this we are going to get as around 66. This is around 90 degrees because cos 90 is 0. And this will be 114 degrees and this will be 145 degrees like you are going to get. So this is what space quantization. That is, we note that L can never be aligned exactly parallel to anti-parallel. It is always anti-parallel to B. Okay. So this is what we have the space quantization. Okay. This is the space quantization which we have. Now we'll see the electron spin. Okay. See about electron spin here. Electron spin. Right. Next, we'll see how the electron spin will be there. Electron spin. Right. So before calculating the electron spin, when we kept in this, we will study about this what we call Bohr-Sommerfeld theory. The Bohr-Sommerfeld quantum theory, which has been given that the orbits whichever we have, it has been assumed that elliptical orbits has been given by the Bohr-Sommerfeld quantum theory. So this elliptical orbits with relativity correction was in pair with what we call agreement with the observed values of the fine structure. That is the fine structure of hydrogen spectral lines. So that is what we have this given by the Bohr-Sommerfeld theory. But there are some drawbacks in the case of the Bohr-Sommerfeld theory. First, what we have in the drawback in the Sommerfeld Bohr-Sommerfeld theory is that, for example, what we call is it could not be applied for the spectral lines which are having the atoms other than hydrogen. That means uh, this Bohr-Sommerfeld quantum theory successfully explained for hydrogen atom, which is having single electron in that one. But if you are having more than one electron, that is other than the hydrogen atom, this Bohr-Sommerfeld theory does not explain the fine structure of the what we call atoms. So that is one drawback which we have in the case of the Bohr-Sommerfeld theory. What is that is? It does not explain the spectral lines of atoms other than hydrogen atom. Okay, fine structure of the uh, atoms which are having more than one electron, it does not explain. That is one drawback which we have in the case of this electron spin. And one more drawback which we have is, suppose if you keep what we call this atoms in any magnetic field, what will happen means it is going to be see what we call splitting of spectral lines. Okay, splitting of spectral lines into 4 and 6 and more components. That is nothing but whenever we keep this atom in a magnetic field, it is going to be split into different energy levels. That is what we call it as a Zeeman effect, anomalous Zeeman effect. So this anomalous Zeeman effect, which is not explained by this Bohr-Sommerfeld theory. So first one is the atoms which are having more than what we call greater than one electron if we are having. So one electron, if you are having more than one electrons, like 2, 3, whatever we are going to be have. So the what we call fine structure, the fine structure that is nothing but which is going to be split into again different lines. So this fine structure of the electrons which are having more one electron is not explained by this Sommerfeld theory, and as well as it does not explain the anomalous Zeeman effect. Okay, anomalous Zeeman effect. That is nothing but splitting of this spectral lines when we keep this atom in a magnetic field. These two does not explained by this Bohr-Sommerfeld theory. Okay. So later on, these drawbacks, whichever we are having, has explained whatever may be the drawbacks which are occurred in the Sommerfeld theory, successfully explained by Uhlenbeck. He proposed, Goudsmit and Uhlenbeck in the year 1925, they have been proposed that an electron must be looked upon as a charged sphere spinning about its own axis. That means whenever it is spinning about its own axis, it should be considered as a charged sphere. Okay, having what we call angular momentum and consequently magnetic dipole moment. Okay, so that is these are called what we call spin angular momentum S. We are going to be called spin angular momentum S, and spin magnetic dipole moment mu S we are going to be called. That means they have taken that whenever this what we call electron, it can be taken it as a charged sphere they have taken whenever it is spinning on its own axis. So from that, it is going to be having this what we call angular momentum S, as well as this spin magnetic dipole momentum mu S you are going to be have. Okay. So these, by taking these S and mu S, they have been explained the electron spin here. So here, suppose if you consider, let us consider that the magnitude of S of the spin angular momentum of the electron in terms of a spin quantum number. Okay. So this S in terms of the spin quantum number, if you write, so we can write this S as S is equals to, we can write this small s, S into S plus 1 into H by 2 pi into H by 2 pi we can write. So the only values with which the spin quantum number can be given is S is equals to half we have. Okay. So which confirms the observed fine structure, that is nothing but splitting of a single line into doublets. Okay, splitting up this line into doublets. So by taking S is equals to half. So what we'll get, S is equals to root of half into half plus 1 into we have h by 2 pi. H by 2 pi. So which you are going to get it as uh, root 3 by 2, root 3 by 2, root 3 by 2 into h by 2 pi into h by 2 pi you are going to get. Right, s is equals to half into half plus 1 into h by 2 pi, which you are going to get as a root 3 by 2 into h by 2 pi. So the components of S along the magnetic field that is parallel to the z direction. So therefore we can write this as parallel to the z direction. So this we can write it as a Sz, which is equals to ms into h by 2 pi. H by 2 pi. So here we have got this as S is equals to what we have got, root 3 by 2, H by 2 pi we have got, and this parallel to this Z direction, Sz, we can write it as Ms into H by 2 pi we can write. So one we have got Sz is equals to Ms into H by 2 pi, and this S is equals to root of 3 by 2 into H by 2 pi we have got here. So this Ms, whichever we have, this is the spin magnetic quantum number. Ms is nothing but spin magnetic quantum number, and it takes the values. Ms is nothing but spin magnetic quantum number, and it takes the values like 2s plus 1. It is going to be 2s plus 1. So 2s plus 1 means if you substitute s is equals to half here, because the spin we have taken it as a half. So you are going to get 2 you are going to get. That means it can takes two values. Those are plus s and minus s, which is going to be taken. That means ms value is equals to plus half, and we have another value is minus half we have. That is, the spin of the electron should be plus half or minus half. When we consider the spin of the electron is plus half, so this Sz is equals to, we will be getting it as what, 1 by 2 into h by 2 pi we are going to get. When we consider this as a minus half, this Sz value you are going to get it as minus half into h by 2 pi you are going to get. Okay. So thus, it has been concluded from the experimental data that the gyromagnetic ratio for electron spin is mu s by s. Mu s by s is twice the corresponding ratio. Mu l by l is twice the corresponding ratio mu l by l. So mu l by l we have got it as a E by 2m. So for the electron orbital motion, right? So here, right. So E by 2m, mu L by, so this mu L by L is equal, so we have got mu L by L is equal to E by 2m we have got for the electron orbital motion. So thus the spin magnetic moment mu s of the electron is related to the spin angular momentum S, capital S. Okay. So therefore we can write mu S is equals to minus 2 into E by 2m into S. Okay. So thus the spin magnetic momentum mu S of electron is related to the spin angular momentum S, which is given by mu S is equals to minus 2 into E by 2m into S we have. So here the minus sign, which is indicates that mu S is opposite to the direction of S, okay, because electron is negatively charged. So here it is usual to write call, right. So it is usual to write the relation mu s is equals to minus gs into E by 2m into s. Okay. So where gs value is equals how much? Its value is equals to 2 here. So gs is called it as what? Spin g factor we are going to be called here. Okay. We can express this spin magnetic dipole moment in terms of the Bohr magneton. We can express this spin. Right. Right. So we can express this spin magnetic dipole moment in terms of Bohr magneton. So we have a mu b is equals to E h by 4 pi m. This already we have derived Bohr magneton. Okay. So therefore we can write s is equals to minus gs into this is a mu b by h by 2 pi into s we can write. So here in place of this E by 2m in terms of mu b we have written, so that we have got mu s is equals to minus gs into mu b by minus h by h by 2 pi into s that we have done. So if you rewrite this equation, we will be getting it as minus gs into mu b by h by 2 pi into this s value we are writing here, that is ms into h by 2 pi. Already in the from the previous equation, we'll get this ms into h by 2 pi. So therefore, we can get this as, okay, this we can get it as mu s, which is equals to, so here it will be minus gs into mu b into ms we are going to get. So this h by 2 pi, this h by 2 pi get cancels. Mu s is equals to minus gs into mu b into mb we are going to get. So we know that gs value is that is spin g factor is equals to 2 we have. And ms, it is going to be take two values like a plus or minus half value. It is going to be. So therefore, we can write mu s along the z direction, mu s along the z direction as plus or minus mu b we can, because the values, if you substitute gs is equals to 2, if you substitute ms is equals to half, if you substitute, just say here, we'll write here. Suppose mu s is equals to ms, gs value I'm taking it as a 2, and mu b as it is I'm writing, and the ms value I'm writing it as a plus half if I write. So 2 get cancels, we'll get a mu s is equals to minus mu b you are going to get. And similarly, mu s you are going to get it as in another case plus mu b you are going to get. These are the two cases. That is what we have written here. So that mu s is equals to plus or minus mu b you are going to get. That means the spinning electron proved to be successful in explaining not only the fine structure and anomalous Zeeman effect. Okay, anomalous Zeeman effect. So whatever may be the drawbacks which we said, which are not given by this Sommerfeld Bohr quantum theory, that is the fine structure of this electrons which are having more than one. So this is what we discussed. The electrons which are having what we call more than one electron, for those how the fine structure is getting that not explained by this Bohr-Sommerfeld theory, that was successfully explained with the help of this what we call Gaudsmit and Uhlenbach theory, which is given by this what we call electron spin concept. And as well as this anomalous Zeeman effect, that is whenever we keep this atom into a magnetic field, the splitting of these lines, how it is going to be possible, that is also explained here. This is what we have, what we call electron spin. So electron spin, whenever it is revolving on its own axis, we have to take it as a charged sphere. Okay, so that is how we can explain. Now just we'll see about next one, that is a vector atom model. Okay. So next we'll see the vector atom model. Vector atom model. Vector atom model. Right. So that in this vector atom model, the total angular momentum of an atoms results from the combination of the orbital and spin angular momentum. That is nothing but total angular momentum, which is a combination of both the orbital angular momentum plus spin angular momentum. Spin angular momentum. Right. Total angular momentum is the combination of this orbital angular momentum and spin angular momentum of the electrons. Since the angular momentum is a vector quantity, we can represent the total angular momentum by means of a vector, okay, which is obtained by the addition of this orbital angular momentum as well as the spin angular momentum vectors. So this will lead to the what we call vector atom model. So generally we will consider that an atom whose total angular momentum is provided by a single electron here. So the magnitude of this orbital angular momentum is given by this L. Okay, the magnitude of the angular momentum L of atomic electron, which is given by L is equals to root of L into L plus 1 into H by 2 pi into H by 2 pi. Okay, and it's Z component along the Z, which is given by LZ, which is equals to ML into H by 2 pi. Okay, so this small l here, it is nothing but orbital quantum number. Small l is orbital quantum number. Small l is orbital quantum number, and ML, whichever we have, this ML is the corresponding magnetic quantum number. It is a magnetic quantum number which we have. And the values of this ML, which it can takes, L, comma, L minus 1 and so on up to 0. That means 0, L minus 2, L minus 1 up to L it is going to be take. And in this side and so on, minus L plus 1, comma, minus L. Okay. So 0 to left positive values like up to L values, and in this side up to minus L it is going to be takes place. Similarly, we can write the spin angular momentum S also. Spin angular momentum S, which is given by S is equals to root of S into S plus 1 into H by 2 pi we can write. And Z component of this we can write it as SZ, which is equals to MS into H by 2 pi we can write. H by 2 pi we can write. And we know that the magnetic spin, the MS value will be like MS value will be plus or minus half we are going to be have. Okay, MS is equals to plus or minus half, which is equals to plus or minus. Yes, we can write. This is what the orbital quantum number and spin quantum number which can takes place. Okay, now we will write the total angular momentum of the electron, the total angular momentum of the electron, which is represented with the J. It is a combination of both the spin angular momentum and as well as the orbital angular momentum. That is orbital angular momentum L and spin angular momentum S here. So J, we can write J, we can write it as magnitude of, we can write it as J into J plus 1 into H by 2 pi we can write. And similarly, Jz, which we can write it as Mj into H by 2 pi we can write. Mj into H by 2 pi we can write. And as well as the values of Mj. Okay. J is here. J is called it as what? Inner quantum number, and Mj is corresponding magnetic quantum number we are going to call here. And this Mj values and the Mj which it going to takes the values is Mj, it is going to take the values as from 0 if you take towards this J minus 1 and as well as this J you are going to have. And in the negative side, minus J comma minus J plus 1 comma minus J it is going to be have. So the relationship among these uh, various angular momentum quantum numbers, since Jz, Lz and Sz are scalar quantities, we can write Jz is equals to Lz plus or minus Sz we can write, and similarly this Mj we can write it as Ml plus or minus Ms we can write here. And we know that Ms, Ml is an integral and Ms is equals to, Mj is equals to combination of this Ml, right? Ml plus or minus Ms we have. And this Ml is a integer. It is an integer, and Ms value that is going to takes only two values like a plus half and minus half. So we can write plus or minus half we can write. So therefore, from these Mj is also going to be an half integral. Okay, because Ms value we have plus or minus half. So if we substitute in this Mj value which you are going to be get, so this Mj is must be a half integral. Okay, it must be a half integral. The maximum values of Mj, Ml and Ms are JLS respectively you are going to be have. So therefore, as we have taken previous expressions, so we can write a J is equals to L plus or minus S we can write. L plus or minus S we can write. Like Mj, J is also half integral you are going to be have here. Okay. Suppose if you take here, right. So since J, L, S are quantized, that is capital J, capital S are quantized, they can have only certain specific relative orientations in case of one electron atom, so there are only two relative orientations are possible. What are those two relative orientations which are possible corresponding to this is J is equals to L plus S one case and J is equals to L minus in another case. So in this J is greater than L. In this case, J is less than L. You are going to be having. Okay. So it is going to take these two values. It is going to take. Right. So the two ways in which the two ways in which L and S can combine to form J is when L is equals to 1 and if you take S is equals to half. Suppose if you take L is equals to 1 and S is equals to half. So in this case, J is equals to, you'll get L plus S one case, which is 1 plus 1 by 2. It should be 3 by 2. In one case, you are going to get. In another case, J is equals to L minus S you are going to get. So in which L value is 1 and minus half. So you are going to get it as a 1 by 2 you are going to get. So if you see the what we call graphical notation, that is how this will be there. So J will be in this direction. L and S. Okay. So this is a J. This is J. This is L. This is S. So this is for J is equals to L plus S. And for J is equals to L minus S in this case, because this is the direction of this J, L will be in this direction. And from here, we have S. So this is in the case of J is equals to L minus S. So the angular momentum of the atomic electrons, L and S interact magnetically, so which is known as spin orbit interaction we are going to be called. So they exert what we call torque on each other. These internal torques do not change the magnitudes of the vectors L and S, but causes them to precess uniformly around the resultant J, around this resultant J. So that means they are going to be revolved around this one. So this is what we have the vector atom model. Okay, this is a vector atom model. So in this vector atom model, we have taken this J is equals to combination of L and S. Okay, J is combination of L and S. J is nothing but the total angular momentum of an atom, which is resulting by the combination of these two, that is orbital angular momentum and the spin angular momentum. So that is the reason why we have written J is equals to L plus S. And individually, we have written the what we call L value, that is L is equals to, we have root of L into L plus 1. So L is equals to root of L into L plus 1 into H by 2 pi. And along the Z component, we have written that Lz is equals to ML into H by 2 pi we have written, and it can takes the ML values like from 0 to L into L minus 1 L, and here minus L plus 1 minus L. Similarly, the magnitude of the spin angular momentum we have written S is equals to root of S into S plus 1 into H by 2 pi. And Z component we have written as Z is equals to MS into H by 2 pi, and MS can take only two values like MS is equals to plus or minus half, and S is equals to, it is going to be have plus or minus half values. So this is what S we have. Then we have taken the total angular quantum number, that is a total angular momentum we have taken, that is a combination of J is equals to L plus S. J is equals to L plus we have taken, L plus S we have taken. So therefore, J also we have written, under root of J into J plus 1. J into J plus 1 into J by 2 pi, and L is equals to root of L into L plus 1 minus L. Similarly, the magnitude of the spin angular momentum we have written S is equals to root of S into S plus 1 into H by 2 pi, and Z component we have written as Z is equals to ML into H by 2 pi, and that? Here. So we have written J is equals to under root of J into J plus 1 into H by 2 pi. And similarly, this along the Z component, JZ is equals to MJ into H by 2 pi. We have written. Okay. So then we have got the total angular quantum number we have got, and we have given that the values. Okay, this is what we have the total angular momentum quantum number we have. Okay, so this is about the total angular quantum momentum number.